Imagine lowering the temperature of your home by as much as 25 degrees. Without an air conditioner, without refrigerants, without a compressor, and without receiving a painful electricity bill at the end of the month. Now imagine that this technology isn't new. It's not experimental. It's not hidden inside a research laboratory. In fact, humans have been using variations of it for more than 4,000 years. And yet, despite rising energy costs, heat waves, and growing concerns about power grid failures, most people have never heard of it. Why? If this technology works so well, why do we stop using it? And who benefits from keeping it forgotten? Today, we're investigating one of the most fascinating cooling systems ever developed, a technology built from nothing more than clay, water, and an understanding of physics that ancient civilizations mastered thousands of years ago. And the deeper we dug into this story, the more surprising it became that if you enjoy documentaries about forgotten technologies, hidden engineering, self-sufficiency, and the inventions history almost left behind, make sure you're subscribed. Because some of the most important solutions to modern problems may already exist. We simply forgot where to look. Every summer, the same cycle repeats itself. Temperatures climb. Air conditioners switch on. Power grids strain under enormous demand. And millions of people watch their electricity bills skyrocket. Modern cooling has become so normal that most of us rarely question it. We assume air conditioning is the inevitable endpoint of technological progress, the best solution humanity could invent. But what if that assumption is wrong? What if another path existed? A path that required dramatically less energy. A path that produced no chemical refrigerants. A path that could operate even during a power outage. Because hidden in deserts, palaces, ancient cities, and forgotten architectural traditions is evidence that another cooling technology once flourished. And unlike many historical inventions, this one didn't disappear because it failed. It disappeared despite working remarkably well. Which raises an uncomfortable question. If it was effective, why did we abandon it? To answer that, we need to travel back thousands of years. To a place where staying cool wasn't about comfort. It was about survival. Picture the deserts of ancient Persia. Temperatures routinely exceeded 100 degrees Fahrenheit. Water was scarce. Shade was precious. And there was no electricity. No fans. No compressors. No air conditioning. Yet entire cities survived. Not only survived, but thrived. The people living there faced a problem that modern engineers still struggle with today. How do you create comfort in extreme heat while using as little energy as possible? The answer emerged from a simple observation. Builders noticed that porous clay vessels filled with water felt cooler than their surroundings. Something unusual was happening. Water slowly seeped through microscopic pores in the clay and evaporated from the outer surface. As it evaporated, it carried heat away. The clay cooled. The surrounding air cooled. And suddenly, an idea was born. Throughout the Middle East, builders began incorporating cooling principles directly into architecture. Structures known as mashrabiyas appeared. In India, intricate stone screens called jalis served a similar purpose. These weren't merely decorative features. They were engineering devices. Passive cooling systems hidden in plain sight. But this was only the beginning. By around 400 BC, Persian engineers took the concept to an astonishing new level. They built enormous structures known as yakshals. Massive mud brick domes rising nearly 60 feet into the sky. At first glance, they looked like monuments. But they were actually giant refrigerators. In the middle of scorching desert climates. Without electricity. Without machinery. Without fuel. Using sophisticated combinations of windcatchers, underground chambers, insulation, and evaporative cooling, these structures could produce and preserve ice throughout the year. Think about that for a moment. Ice. In the desert. More than 2,000 years before modern refrigeration. The achievement was extraordinary. And as civilizations traded knowledge across regions, these cooling techniques spread, eventually reaching the Indian subcontinent. There, Mughal architects expanded and refined the concept. Water houses, ice houses, subterranean cooling chambers. Entire architectural traditions emerged around the idea that water and earth could manipulate temperature naturally. The science was understood long before the scientific terminology existed. But then something happened. A technological revolution changed everything. and one ancient cooling method after another began fading into obscurity. Fast forward to 2017. An architect in New Delhi named Monish Sirapurapu faced a modern problem. An electronics factory was generating intense heat. Temperatures near a large generator had reached approximately 122 degrees Fahrenheit. Conventional cooling solutions were expensive, energy-intensive, and ineffective in that specific environment. So Sirapurapu looked backward instead of forward, toward ancient cooling principles, toward clay, toward evaporation. What emerged became known as the beehive terracotta cooler, and its operation relies on one of the most powerful cooling mechanisms found in nature: evaporation. Every time sweat evaporates from your skin, your body cools. The same process powers this entire system. But the engineering behind it is surprisingly clever. Terracotta is filled with microscopic pores, tiny channels invisible to the naked eye. When water is introduced, these channels pull moisture throughout the clay through a process called capillary action. Think of it as millions of miniature pipelines. Water continuously migrates toward the surface, keeping the entire structure damp. Now comes the important part. As warm air passes across that wet surface, water molecules absorb thermal energy and escape into the atmosphere as vapor. That phase change requires heat, and the heat comes directly from the air. The air cools. Simple. But the beehive design takes things further. Much further. Instead of using a flat wall, hundreds of terracotta tubes are stacked together in a honeycomb pattern. Why? Because surface area is everything. The greater the surface area exposed to airflow, the greater the cooling potential. The honeycomb geometry dramatically increases the amount of clay interacting with moving air. And then another piece of physics enters the picture. As air enters the narrow tubes, it accelerates. This creates turbulence. Instead of flowing smoothly past the surface, air repeatedly collides with the wet clay. Each collision transfers more heat. Each transfer fuels more evaporation. And because the channels are narrow, the airflow speeds up. This is related to a phenomenon known as the Venturi effect. Faster airflow encourages faster evaporation. Faster evaporation creates greater cooling. The system effectively amplifies itself. By the time the air exits the structure, it can be dramatically cooler than when it entered. No compressor, no refrigerant, no complex electronics. Just geometry, clay, water, and physics. But theories are easy. The real question is whether it actually works. And that's where the numbers become fascinating. In the factory installation that inspired worldwide attention, temperatures were reduced from approximately 122 degrees Fahrenheit to around 97 degrees. That's a drop of roughly 25 degrees. Enough to transform an unbearable environment into a workable one. But temperature reduction was only part of the story. The energy savings were even more remarkable. Traditional air conditioning systems rely on compressors, motors, refrigerants, and continuous electrical input, all of which consume significant energy. The terracotta system required only a small water circulation pump. Its power consumption was tiny by comparison. Measurements indicated energy reductions approaching 80% compared with conventional cooling methods for similar applications. Think about what that means. As energy prices rise around the world, cooling demand continues increasing. Heat waves are becoming more frequent. Electrical grids are facing greater stress than ever before. A technology capable of reducing cooling energy demand by such a large margin would seem impossible to ignore. Yet most people have never seen one. Why? Because this story has a twist. And it's a major one. At first glance, the beehive cooler appears almost perfect. Cheap. Sustainable. Efficient. Beautiful. Ancient wisdom meeting modern engineering. But reality is more complicated. The first limitation is climate. Evaporative cooling depends on water evaporating. That means dry air is essential. In arid regions, the system performs exceptionally well. But in humid environments, evaporation slows dramatically. And when evaporation slows, cooling performance drops. This is why evaporative coolers thrive in deserts, but struggle in tropical climates. The second challenge is building design. Modern homes are often sealed tightly. They are designed around mechanical heating and cooling systems. Fresh air enters through controlled ventilation. The Beehive cooler operates differently. It requires airflow, continuous airflow. The building itself must work with the cooling system rather than against it. And then we encounter a less obvious obstacle. Economics. Modern air conditioning supports a vast global industry. Manufacturers, installers, maintenance companies, replacement parts, annual servicing, entire business ecosystems. A conventional air conditioner contains hundreds of components. Many eventually wear out. Many require replacement. Many generate recurring revenue. A terracotta cooling wall is different. It contains very few moving parts. It can last for decades. And in some cases, portions can be built using locally sourced materials. From a business perspective, that changes the equation a lot. Then there are regulations. Building codes often favor standardized technologies. Systems that fit neatly into existing categories. Systems with established efficiency ratings and certification frameworks. Innovative passive cooling approaches frequently fall into gray areas. Not because they don't work, but because they don't fit conventional assumptions. And suddenly we begin to understand why such a promising technology remains relatively rare. Not because it failed, but because modern infrastructure evolved around different priorities. So should everyone rush out and replace their air conditioners? Not exactly. The reality is more nuanced. For people living in hot, dry climates, evaporative cooling can be incredibly effective, particularly for workshops, greenhouses, courtyards, semi-open structures, industrial facilities, and carefully designed homes. For people living in highly humid regions, however, expectations must remain realistic. Mechanical cooling may still be necessary. The future may not involve choosing one technology over another. Instead, it may involve combining them, using passive cooling whenever possible, reducing dependence on energy-intensive systems, and reserving mechanical air conditioning for situations where it is truly needed. In many ways, that hybrid approach mirrors how ancient builders thought. They didn't fight nature. They worked with it, using design, materials, airflow, and physics before turning to more resource-intensive solutions. And that philosophy may be more relevant today than ever before. Why did this technology disappear? The answer is surprisingly simple. It didn't disappear because it stopped working. It disappeared because modern society chose a different path. A path built around electricity, mechanical systems, standardization, and industrial-scale manufacturing. But as energy costs rise and climate challenges intensify, many engineers and architects are rediscovering ideas once considered obsolete. And the Beehive cooler stands as one of the most compelling examples. A reminder that innovation doesn't always mean inventing something new. Sometimes it means rediscovering something old, something overlooked, something forgotten. For more than 4,000 years, humans understood how to cool spaces using little more than clay, water, and intelligent design. The knowledge never vanished. We simply stopped paying attention. And perhaps that's the biggest lesson of all. Some of the solutions to our future may already exist, waiting patiently in the past. If you enjoyed this documentary, be sure to like, subscribe, and let us know what topic you'd like us to investigate next. Would you trust a cooling system made from clay and water? Or would you stick with conventional air conditioning? Let us know in the comments. And if you're interested in more forgotten technologies, hidden engineering breakthroughs, and off-grid innovations that challenge everything we think we know, check out the next video on your screen. Thanks for watching.